Good morning, everyone. So, welcome to the course of electronic transport in mesoscopic and nanoscopic systems. So, as I already discussed in the course Semiconductor Device Modeling, electronic transport in mesoscopic and nanoscopic systems is not governed by classical mechanics. So, in classical mechanics, you can basically consider the electron as a particle. And of course, this assumption is valid when your device length is much greater than the mean free path. So, when the device length is much greater than the mean free path, what happens is that the electron undergoes several scattering events when it passes from one contact to the other, and therefore the phase information is washed out. And so, the electron basically behaves as a particle because its phase is randomized, its phase is averaged out. Okay. Now, if the device length or if the length of flow of electrons within the device is less than the mean free path or is comparable to the mean free path, then the electron would basically suffer one or two scattering events or maybe a less number of scattering events when the electron moves from one contact to the other. And therefore, the phase information is not completely washed out or the phase is not completely randomized. And it is in that limit that we cannot consider the electron as a particle, but we have to consider the wave nature of electrons also. Okay, so when the device length is less or comparable to mean free path, the phase information is not completely washed out, and hence we need to take into account the wave nature of electrons. So we need to take into account the wave nature of electrons. In other words, the electronic flow in these cases is governed by quantum mechanical phenomena rather than classical phenomena. So, in this course, what we will do is we will start with the basics of quantum mechanics as far as required from an engineering perspective, and then we would gradually move into quantum transport, which is basically electronic transport, which is governed by quantum mechanics. Okay, so classical transport this one treats electrons as particles. Quantum transport So this is the method which basically accounts for the electron transport while treating the electrons as waves. So this one treats electrons as waves. Okay. So of course, as you can understand that to learn this quantum transport, we actually need to understand some basics of quantum mechanics, but we'll not go into too much detail because the idea is actually to learn quantum transport, learn the basics of quantum transport, and not too much of quantum mechanics. And quantum mechanics, as it stands out, is very confusing subject. And there is a famous quote by Richard Feynman, who is considered to be one of the pioneers of quantum mechanics. And the quote is exactly that if you think that you have understood quantum mechanics, then you actually haven't understood it yet. So the other meaning of this statement is that no one basically understands quantum mechanics completely, and there are a lot of confusions and a lot of work that is going on to unveil the principles of quantum mechanics, to unveil the principles of quantum particles. And there are a lot of experiment that is going on in quantum gravity and all these stuffs. So quantum gravity was in the news a few months back. So we will not again go into very detailed description of quantum mechanics. We will only learn the basics as much as required to basically understand quantum transport. And again, quantum transport also we will only learn the basics in this subject because quantum transport is again a research field, and the only way to know quantum transport is actually to do research in this field, because quantum transport is very vast. So in classical transport we have a few common techniques like the drift diffusion method or the Boltzmann transport method or Drude's model. But quantum transport as it stands out is very vast, and there are a few generic techniques, but these techniques are so general that you cannot really apply it simply to all systems, and really things need to be modified or things need to be worked out by a great extent to redesign these formulations for specific systems. Okay, so that is what quantum transport is, and I repeat again that in this course we will just learn about the very basics of quantum transport, and we will not go into too much detail because as it stands out that a 3-month course on quantum transport is not really able to cover that much detail. Okay, so we'll learn as much as we can. So let us first start with quantum mechanics. So before we actually start, I would like to point out 3 things: that quantum mechanics is all about averages, and you must have heard of the famous description or famous way of explaining that, let us say we have many quantum particles, or electron is, let us say, one of the quantum particles. So let us say that we have many electrons in a box. Okay, and we do not exactly know that what are the states in which these electrons are residing, or we have no idea about what is the energy or what is the momentum or what are the other properties of an electron in this box. Whenever we do a measurement on the system, that property of the electrons basically collapses to one of the eigenvalue or allowed value of the system. Okay, so for example, let us say that I do a measurement for momentum of the electron. Okay, whenever I do a measurement on the momentum of the electron, the momentum of the electron, or let us say the electron, would collapse to a momentum which is allowed by the system, which is to say that if I basically prepare an ensemble of identical electrons, that is, I have, let us say, 3 such completely identical bodies which contain electrons. Of course, I am showing the electrons as particles here, but these are not actually particles. I am just showing this for convenience. So these 3 boxes which contains electrons are identically prepared under the exact same hypothetical situation, and if I do a measurement on these 3 systems under the same condition, of course these measurements would not yield identical results. Okay, let us say I am measuring the momentum of the electrons on all these 3 boxes which are identically prepared. In that case also, the measurement would not give me the same result. Whenever I do a measurement, the momentum of the electrons basically collapses to a momentum which is allowed by the system. Now, this box allows a large number of values of the momentum, and it would be clear very shortly or very soon that this box basically allows a large number of values of the momentum, but it does not allow any value of momentum. So there are a large number but specific values of momentum which this box can allow. Okay, so let me write it here. There are a large number or maybe infinite number of specific values of momentum that this system allows, and whenever we do a measurement, the system basically collapses to one of the allowed values of the momentum. So when we do a measurement of momentum, the system collapses to one of the allowed values of momentum. Now, because there are a large number of specific values of momentum, okay, the system can collapse to any one of the values. So we do not know which value of momentum the system would collapse to, and if we do a momentum measurement on these 3 identically prepared system, then we will get different values of momentum. Or let us say that if we do repeated measurement on even a single system, so I do a measurement on this system, I again take back this system to the initial state and I again do the measurement of momentum, and I again take back this system to the initial state, I again measure the momentum. The measurement result in each case would be different, and we do not know in advance that what would be the outcome of the measurement. Okay, it would be one of the allowed values of momentum in the system. Okay, so how do I understand that what is the actual momentum? So the actual momentum or let us say that we cannot actually define what is the actual momentum, but the average momentum of the system is actually the average value of all these measurements. Okay, so we cannot say that this system is at momentum p1 or this system is at momentum p2, but all we can do is that we can make repeated measurements on identically prepared system and conclude the average momentum. Okay, so that brings me to the first point, that quantum mechanics is all about averages. We actually do not know what is the actual momentum, or to be more specific, the system is not at a specific value of momentum, but the system is residing at many momentum states all at once, and this is known as overlap of wave functions. Okay, this is something that is not allowed in the classical world. In the classical world, if a particle is basically moving with a given velocity v and it has a mass m, then we call that the system has a momentum m times v. Okay, but in the quantum world, we cannot really always specify that what is the given value of a property of a system. We cannot know what is the given value of a property of a system, or let us say even if we have one particle or one electron, that electron can actually reside in a state which is the overlap of many states. Okay, these things would become clear as we move through the course. Right now it might seem a little bit confusing. Okay, and the allowed values of momentum, the allowed values of momentum or any property are known as the eigenvalues. The allowed values of momentum are known as the eigenvalues of the momentum operator. Okay, so also my second point is now clear, that in quantum mechanics a single particle or a single electron can reside in the overlap of many different states. Okay, again this is something which is not allowed in the classical world. In the classical world, if a particle is moving with a velocity v and it has a mass m, then the momentum is m times v. In quantum world, a particle can reside in a state which is basically the overlap state of momentum p1, p2, p3, p4. So whenever I do a measurement on momentum, the system would basically collapse to one of the momentum state. Whenever I do a measurement of momentum, I can get either p1 or I can get p3 or I can get p4 or I can get p2 also. I do not know what will I get. Okay, so these things again is a little bit confusing at first, but as we move through the course, this thing would become more and more clear. Okay, now to give you a very simple example that why we can't actually measure the position with 100% accuracy or the momentum with 100% accuracy. So let us say that in the classical world, how we actually denote a particle is that it has a definite shape and it occupies a definite volume and it has a definite mass and it is moving at a definite velocity v. So the momentum is basically mv. Now in the quantum world, since things are wave functions, okay, since things have a wave nature and a particle nature, we cannot actually determine the exact position or the momentum. or even other properties. So for example, let us consider that we have a sine wave like this. Okay, this is, let us say, the electron wave function, and okay, so the electron wave function is basically given by psi, which is basically a sine kx. This is just an example. It is not necessary that the electron wave function has to be given by this form. So let us say that we have a sinusoidal wave function. This is the time axis, and this is somewhere our 0 level, and this is the actual value of the wave function. So this is basically psi. Okay, now can you really tell what is the exact value of the position of the particle? Not really, right? Because it is spread out. Okay, the particle has some amplitude here. So let me change the color. So the particle has some amplitude here, not amplitude, but some value here. It has some value here. It is again existing at this point, this point, this point. So it is basically spread out. Okay, if this is an electron, and this denotes the wave function of an electron, so this electron is basically spread out over the entire range. So this horizontal axis is not time, but it is basically x actually. So this particle is basically having a wave nature also, and it is spread out over the entire x axis. So it does not have a definite position. So if we do a measurement, we cannot really say that we will find the particle here, or we will find the particle here, or we will find the particle here, because it is existing everywhere. It is spread out in space. So whenever we do a measurement, this particle would collapse at a particular position. Okay, and all we can tell is actually the probability that this particle is present at that position. Okay, I again repeat that since this particle is spread out throughout the space, we cannot say that this particle exists at any given position, but whenever we do a measurement, this particle would basically collapse at a given position. It can collapse either here, or it can collapse here, it can collapse anywhere basically. And so what we can say is the probability, or what we can conclude is the probability of finding this particle at a given position after measurement. Okay, and whenever we have probability, we also have average. So what we can say after repeated measurement is the average value of x at which the particle is residing, or the average value of position of the particle. Okay, so just as I said, we again go back to the same statement that quantum mechanics is all about average. But note that although this wave function does not have a definite position, it has a definite momentum actually, so which is related to this k vector. It's not a vector here because we are only having one dimension, but which is related to this k number over here. And we know that the momentum of a particle, of an electron, is given by h cut k. Okay, now because this particle has a definite value of k, this has a definite momentum, but this does not have a definite position. Okay, so this brings us to one part, or the layman's view on the uncertainty principle, that we cannot really measure both position and momentum with 100% accuracy. In this case, in the case of the sinusoidal wave function, the momentum is fixed, or we can measure the momentum with 100% accuracy, but we cannot measure the position with 100% accuracy because it is spread out. On the other hand, let us say that we have a particle at a definite position. So this horizontal axis is x, and this is the amplitude of the particle or the wave function psi, and let us say that the wave function looks somewhat like this, like a delta function basically. Okay, so it's a delta function, and here we can say that this electron or this quantum particle has a definite position, okay, at x equal to x0, if this point is x0, that is. Okay, so we can measure this position with 100% accuracy, but we cannot measure the momentum because electron is actually a wave, or quantum particles are actually waves. So if we do an analysis of this particle here, we have to think in terms of waves. And what is the Fourier transform of the delta function? The Fourier transform of the delta function is 1, which means that this delta function consists of an overlap of sinusoidal components of all frequency. Okay, so this particle psi, or this wave function psi, is existing as an overlap of all the momentum states. Okay, because if we transform it into frequency space, it is the Fourier transform is 1, which means that there are numerous and continuous value for all the momentum states or all the k states. Okay, so Fourier transform, when I do the Fourier transform, I do from x space, which is the position space, to k space. K is basically the momentum space. Okay, and you already know how to do Fourier transform, so I am not going into too much detail. If you do not know, I would really advise you to revisit the Fourier transform, because Fourier series and Fourier transform are very closely related with what we are going to do, and it is required to understand this course, at least the first few classes. Okay, so we do this Fourier transform from x space to k space. Okay, so this particle, which is of the form of a delta function, has a particular position, but it does not have a particular value of momentum because it is existing as an overlap of all the k states. Okay, so this particle has a definite position but no definite momentum. Now let us consider another case to just give you a more detailed idea. Let us consider this particle which is residing in space x, and its wave function looks like this. So it's kind of a Gaussian wave function, or it resembles the Gaussian function. So in this case, this particle is spread out throughout the space because it exists here, it exists here, and it also exists here. Of course, the probability that the particle exists at this point is more because the value is more, and the probability that the particle exists here is lesser because the value is lesser. We'll actually see how wave function can be related to probability later, but right now just satisfy yourself with this explanation. Okay, so it does not have a definite position. If I measured the position repeatedly, I would get a large number of values actually. Okay, different values. Okay, and it does not also have a definite momentum, because to have a definite momentum, the wave function should be of the form a sin kx or a e to the power I kx. Okay, if the wave function is of this form, then we can define a definite momentum of the particle, but because this is actually a wave, okay, this is not a classical particle, this is actually a wave. So to define the momentum, we have to get the expression in this form or in this form. But this is a Gaussian shaped function, so this is not a sinusoidal function, so it also does not have a definite momentum, but it again can be, this function can be broken down into its Fourier components, and we can say that this particle or this wave function exists as an overlap of its Fourier components, that is the momentum states. Okay. This is the case that this particle does not have definite position because it is spread out throughout space, does not have definite momentum or definite sorry, it does not have a definite position because it is spread out throughout the space, and it also does not have a definite momentum because it is not exactly a sinusoidal wave, or it is not in the form of a sinusoidal wave. Okay. So in the quantum world, we cannot always determine the position or the momentum with 100% accuracy, and we can never determine both position and momentum with 100% accuracy. Okay, and that is what the uncertainty principle was about. You have studied about this uncertainty principle in your high school. If you do not remember, please revise it a little bit. It would just take 2 minutes. Okay.